you have sex chromosomes, which are some combination of X and Y. You also have autosomes, which are chromosomes 1 to 22 for a human. Everything that we have discussed so far is inheritance if the gene was on an autosome, on chromosome 1, 2, 3, 4, 5, 6, 7, all the way up to 22. What I'll show you now is what it looks like if a gene is on the X or the Y chromosome. Just to remind you, your typical male will have one X and one Y chromosome. Now, I am ignoring scenarios here where there is a different number of sex chromosomes, like Turner syndrome and Klinefelter syndrome. We are talking about the typical male, one X, one Y, and females who typically have two X chromosomes. So one of the first times that we realized that it made a difference if you were male or female was studying Drosophila the fruit fly. In Drosophila, white eyes are on the X chromosome and are recessive. So the allele for white eyes is on the X chromosome and it's recessive. So this gives us a slightly different scenario depending on if the offspring is male or the offspring is female. Females need to inherit two copies. So they would need to get two X chromosomes that both had that recessive allele for white eyes. When we're talking about sex-linked inheritance, we usually write the allele as the letter of the chromosome. Most of the time it's the X chromosome, with a little superscript with the letter that represents the allele we're talking about. Males only need one copy. Now here's why. Females have two X chromosomes. For them to get a recessive characteristic, they can't have the dominant version on their other X chromosome. They absolutely have to have two copies. But since males only have one X chromosome, normally, if they inherit even one copy of the recessive allele, they will show that phenotype because there's no second X chromosome to give me a different possibility. The result is that very frequently males are more affected if the allele is on the X chromosome. Now, it's possible for an allele to be on the Y chromosome, but it is not the usual case. The Y chromosome is very small and doesn't contain very many genes. And so I would say 96.8% of all of the sex-linked inheritance that we would ever see is because of something that is on the X chromosome. And the fact that more males are affected if the allele is on the X chromosome is a really, really good way to look at something and ask yourself, do I think this is sex-linked? If I were to show you a family tree, and out of all 30 people on the family tree, the only people who had a characteristic that we were studying were male, that would be really good evidence that it was sex-linked. If some males and some females had it, but the number of males was still way higher, that would still be pretty good evidence. If no females showed the characteristic and only males did, that would be pretty sure evidence that it was sex-linked. So the example that we're going to start with is color blindness, specifically red-green color blindness. Is anybody in the room colorblind? Oh, this is the first time. I've always had someone colorblind in my class when I talked about this. From my understanding, people who are red-green colorblind, when they look at traffic lights, see shades, and they can tell which one is which by knowing, for example, that red is it on the left? Oh my gosh, I don't even know. Red, yellow, green. Yeah, I think that's how it goes. Anyways, they're more careful than I am because they can't see which color. They know which order the lights go in. But I had a student once who said they were a different shade. Even though he couldn't see the color, they looked different to him. So for him, red was kind of a darker gray and green was kind of a lighter gray. That's how he described it. And I say he because the only people I've ever known to be red-green colorblind are males. Color blindness is on the X chromosome. So just a little refresher, a little reminder about how things work. If this is your mother and this is your father, there's a particular way that chromosomes are inherited. You might notice the French words for mother and father are there too, a little mini language lesson. Your mother can only give you X chromosomes. So regardless of if we are discussing a daughter or a son, mother can only give X chromosomes. The father is actually the one who determines the gender. The father could give an X chromosome, and the result would be a daughter. Or the father could give a Y chromosome, and the result would be a son. So, little side note here about kings. You might be aware from your studies in social studies that it was not uncommon for a king or someone important to have his wife have her head chopped off or have her banished if she only gave birth to daughters because he wanted a son. Now, he was quite a stupid king if he thought that because it was in no way her fault. Who determines gender? The father. Because the father is the one that has two different sex chromosomes. If the father contributes a Y, the result is a daughter. If the father contributes, an X, the result is a daughter. If the father contributes a Y, the result is a son. So every king who ever had his wife's head chopped off for not having sons should have chopped off his own head because it was his fault. So fathers can give either chromosome. Mothers can only give their X chromosome. That is why we would often say that this type of thing is passed from mother to son. That's not the only way it happens, but it's very common to see a mother pass a characteristic that is X-linked onto her son. So I've got a little Punnett Square over here, and we're going to fill it in with some possibilities. We are going to say that we have a father that has normal color vision. So I'm putting an N for normal. And we're going to say that we have a mother who is heterozygous. She has one copy of the allele for normal color vision and one copy of the recessive allele that would make you colorblind. We would call the mother a carrier. Does she have color blindness? No. She needed two copies of the recessive allele to actually be colorblind. But she has a copy of the allele. She could pass that on to her children. The father, we would say in this case, is unaffected. He only has one X chromosome, and he has the normal allele, so he does not have red-green color blindness. Now, in the offspring, especially when we're talking about sex-linked genes, you have to be careful. Are we talking about daughters or are we talking about sons? Because there is a 50% chance that they will have a daughter, also a 50% chance that they will have a son. And very frequently, when you get a question about something that's sex-linked, we will be specific. What is the probability that their daughter will have such a characteristic? So we're going to fill this in. If I fill this in, daughter possibility number 1 gets 2 copies of the normal allele. Daughter number 2 gets 1 copy of the normal allele and 1 copy of the colorblind allele. Son possibility number 1 gets the normal allele. Son possibility number 2 gets the allele for colorblindness. So if I were to answer this question, I would say 50% of their daughters have that genotype, so they are carriers. And I would say 50% of daughters are unaffected. So notice I didn't say 25% because I'm only talking about daughters. There were 2 possibilities for daughters. One of them was a carrier, one of them was not. For the sons, I would say 50% of their sons are unaffected, and 50% of any possible sons they have would be colorblind. Now, that's how I would answer it if we were asking about a daughter or a son specifically. If I were to ask you, what is the probability that these people will have a son with color blindness? The probability is 25%. So you have to look at the way the question is worded. If I ask, what's the probability that one of their sons will have color blindness, you would say 50%, because half of them should and half of them shouldn't. We were specifically asking about sons. If we ask the question, what is the probability that they will have a son and their son will be colorblind, that's your cue to look at the whole entire Punnett Square and take your percentage out of 4 instead of out of 2.